All right, hello. We're looking at lesson 2.5, velocity, acceleration, and the second derivative. So the math in this lesson is simple if you are very comfortable with the derivative rules by now. Okay. The second derivative is exactly as it sounds. You're just looking for the derivative of the derivative. So you're doing the derivative twice, okay? And the notation is written here. So we have fx, which is the original function, f prime of x, which is the first derivative, and then f double prime of x, which is just the second derivative. Okay, so I can write it either as f double prime x with two little dashes, y double prime, or I can use, so for example, if I have y equals to blah blah blah, dy over dx is the first derivative, and then d2y over dx squared, or x to the power, not to the power of 2, this would represent the second derivative, okay? So just to clarify, this does not mean I'm squaring anything. Okay? It's just to signify the second derivative, whereas this is to signify the first derivative, second derivative, okay? All right, so determine f double prime of 2 for this function. So first off, I find the first derivative, which just brings the 3 down. 3 times a third is 3 over 3. 3 subtract 2 is 1. Or sorry, 3 subtract 1 is 2. This is just the power rule. Bring the 2 down, and then derivative of 3x is just 3. This simplifies down to 3 divided by 3 is 1, right? So this just simplifies down to x squared minus 2x minus 3. Then to find the second derivative, we just do it again. So bring the 2 down. The derivative of 2x is just 2. Okay. Now, f double prime, I forgot to finish this, of 2 is going to be just 2 times 2 minus 2, which is just 2. Okay, that's it. That's all second derivative is. Now, like I said, the math in this lesson is easy. It's understanding what all this means that might be a little bit more challenging. Okay, so first off, let's say the red graph, okay, is our original function. Okay, that is fx. Now, if I wanted to find the first derivative, remember, finding the first derivative means I'm finding the instantaneous rate of change, okay, at every single point. Okay, so for example, if I want to find the instantaneous rate of change at 2, okay, 2, so at this particular point, I need to draw a line of a tangent, okay, and the instantaneous rate of change will be the slope of that tangent, which is the slope of that blue line, okay, and that number is going to be a negative number, right? Because if you look at the line, slope of that line, it's going to be negative. Now, I can't tell you what it is right now, okay, but it looks like it will be a negative number. But if I look at the graph beside it, this is f prime of x, okay? If I look at this graph and I look at 2, and I look down here, it tells me that it's negative 3, which means at 2, the derivative is negative 3, which means the slope of this blue tangent is going to be negative 3, okay? So just to remind you what a derivative means, so these three graphs that are drawn, in fact, let me just tell you right now, just so it helps you make the connection. So without any equations given, the red graph is our original function, okay? The blue graph is our first derivative, and the green graph is our second derivative. Now, why does that make sense? Well, thinking back to advanced functions for a second, the red graph, I don't know the full function, but I know it's a cubic, right? The way it's drawn, it's a cubic function, okay? If I had to differentiate that, find the first derivative using blue, using the power rule, it becomes 3x squared. Well, x squared, isn't that a parabola? Look at the blue graph, that looks like a parabola. If I want to differentiate that again, the second derivative, I get the 2 comes down equals 6x, which isn't that linear? Okay, cubic, quadratic, linear, which makes sense because every time you're using the power rule, the number comes down, so it drops by a degree. Okay? Now, that's looking at it algebraically. Now, graphically, how do these two connect? Well, I just showed you a quick example of -3. Now, if I look at fx, okay, and I look at this point right here, the maximum specifically, and I wanted to find the instantaneous rate of change. So if I drew a tangent at that line, and it is drawn there, you can see that's a zero slope, right? At the highest point, it makes sense. There's no rate of change at the top. If you think about throwing a ball up in the air, that's when it stops. There's no rate of change before it changes direction and starts coming down. So since there's a zero slope, well, what x value is that at? It's at -1. So if I look at the first derivative, at -1, I should have a derivative of 0. And sure enough, at -1, I have a derivative of 0 right there, right? Now let's look back at our original function. Where else do I have a slope of 0? Well, it's pretty much going to be everywhere there's a max or a minimum. So if I look down here now, at x equals to 3, there's a 0 slope as well. If I draw a tangent line, the slope of that line is 0. Now if I look back over at my first derivative, again at x equals to 3, it's at 0. Okay? So that makes perfect sense, okay, with the first derivative 0. Now trying to make sense of everything else is a little bit trickier. So for example, what does this point mean? What does this point? 1, 4, okay? So at 1, the derivative is at -4. Well, that just simply means at x equals to 1, that's where the rate of change, so x equals to 1, so right here, okay, that's where the rate of change is the most negative, okay? So this might get a little bit messy, but so right here, at x equals to -1, you notice that the rate of change is 0, right? If I look at x equals to 0, there's a rate of change. So if I draw the tangent at that line, it's going to be a negative value, but I'm not sure what the negative value is. Let's say it's roughly -2. If I draw that tangent line at x equals to 0.5, it becomes steeper and steeper and more negative, right? So it's saying that at x equals to 1, this rate of change is -4, or the slope of that tangent is -4. After that, it starts becoming less negative, which makes sense because the tangents start looking like this. They start flattening out, don't they? Until they get a slope of 0. Yeah? And then they slowly become positive, which is what happens here. The slope of the tangents all become positive. Now, if I were to further connect this or extend this and look at comparing this graph to this graph now, the second derivative, the same ideas apply. Okay? So if I look at the first derivative, where is that slope 0? Well, it's going to be, the slope will be 0 at x equals to 1. So if I look at the second derivative, is that the case here? At x equals 1? Yep, the slope is 0. Okay? Now, to apply this to real life, now you can read this blurb on your own, but it pretty much summarizes what I just said. To apply this to real life or application questions, okay, how does this all connect? Well, the first graph represents displacement, okay, which is the distance an object has moved from the origin. That's the original function. The second graph represents velocity, so the change of displacement over time, velocity or speed, okay? And the third one is called acceleration. And what does acceleration mean? It's the change of velocity over time, okay? So what's the difference between the two of them? Well, think about driving a car, okay? Displacement is just how far you traveled over X amount of time. Velocity is your speed that you're traveling at. Okay, so if you are driving on the highway and traveling at 100 kilometers per hour, okay, that's your velocity. So let's say you don't change that, you're on cruise control. Then your acceleration is 0, okay, which makes sense because that means your velocity looks like this. At 100, You just aren't, you haven't accelerated or decelerated, so your acceleration is 0. Okay? But what if you are on a ramp merging onto the highway? So I know some of you are driving, but I'm assuming most of you have been in a car, or on a bus or some kind of vehicle. If your velocity goes from 80 kilometers per hour to, let's say, 82 kilometers per hour, then there's a change, right? Okay, so then we can say it's 2 kilometers per hour. You're changing per, let's say, per hour. So your speed is changing at 2 kilometers per hour per hour. Okay? So that's the difference between acceleration and velocity. Now let's apply this. So in terms of the word problems and applying the first and second derivative, it's pretty simple. It's understanding that connection graphically. So we've got a construction worker accidentally drops a hammer from a height of 90 meters while working on the roof of a new apartment building. The height in meters of the hammer after t seconds can be modeled by this equation. Determine the average rate of change. This we all know how to do. Okay, just finding the AROC. We get a negative value. Why does that make sense? It's negative because it's decreasing in height. Find the velocity. So we want to find the velocity, or the instantaneous rate of change, at 1 second and 4 seconds. So we find the first derivative. So s prime is just 0 minus negative, or subtract 9.8t, sub in 1, sub in 4. So at 1 second and 4 seconds, that's the speed in which the hammer is traveling at, which makes perfect sense because 4 seconds, so, oh man, at 4 seconds, so it starts at 90 meters high, right? 1 second and 4 seconds. 4 seconds, it's obviously going to be traveling at a higher speed, okay? Due to something called gravity. When will the hammer hit the ground? So I just took the original function, plug in 0 for height, so a height of 0, okay, and solve for t. So it's saying at 4.3 seconds, so 4.3 seconds, it's going to hit the ground. E, determine the impact velocity of the hammer. What's the speed when it hits the ground? You just plug in 4.3 into the first derivative to get negative 4.2 meters per second. And then determine the acceleration function. So once I know the first derivative, I'm going to find that derivative again. Well, I just get a constant, negative 9.8. Well, in fact, anybody who has taken physics knows that 9.8 is the acceleration due to gravity, negative 9.8. So what this is saying is, as this hammer is falling, the velocity is changing at a rate of negative 9.8 meters per second per second. Okay, so what does that mean? That means, now this is just a really rough example, just to wrap your head around it. So 1 second versus 2 seconds, okay? So let's say this was traveling at negative 10 meters per second, okay? Then after a second later, it's now going to be traveling at negative 19.8 meters per second. Yeah. So every second, it's changing at negative 9.8 meters per second. The speed is. Okay. Example 3. The position of a particle is given by st equals 2, blah, blah, blah. So that's the black graph that's drawn. So I color-coded this. Okay. First derivative is in red. Second derivative is in green. Okay. Now, finding the derivatives, I don't think I need to explain. It's pretty self-explanatory. But we are asked to sketch it. So I sketched it before I did any of this stuff. Okay, so those are my derivatives. So in fact, you can sketch these without even looking at the equations. So using the black graph, if I want to find the first derivative, I look at where the slope is 0. Okay, and so its slope is 0 right there, which means for the first derivative, I'm going to get this point. T equals 0, or yeah, when t equals to 2, sorry, s prime of t will be 0. Then I look over here at the minimum, which happens to be at the same point at 6. Okay, that helps me draw the first derivative. Then I look at the red graph, okay, which is the first derivative. To sketch my second derivative, I look at this point at the bottom. That is where my slope is going to be 0, right? So that means for the second derivative at t equals to 4, I'll get a value of 0. Okay? And I confirmed it by doing the algebraic work over here. So the first derivative will be 3t squared minus 24t plus 36. Common factor, factored it, and I get t equals 6, t equals 2, which is indeed the exact 2 points where the x-intercept should go. That is where the original function had a slope of 0. And then same thing with the second derivative, factored it. So for the green graph, t equals to 4. Okay, x-intercept is 4. Again, that is where the slope of the first derivative is 0. Okay. So I left example 4 blank. Okay. I'll leave that for you to do. And then I'll post this with the solutions. Yeah, take care.